From its perch a million miles away, the James Webb Space Telescope is revealing a universe that's richer and more perplexing than astronomers previously imagined, a cosmos that largely hides behind a veil of dust. As the biggest space telescope in history, James Webb pierces that veil by capturing infrared light. Less energetic than the light our eyes can see, infrared light passes more easily through cosmic dust, and the telescope's 21-foot-wide mirror can collect this light from some of the most distant objects in the universe. As such, no matter where we've pointed James Webb, even in the images taken during commissioning that would last a few tens of seconds, we kept getting these galaxies that we weren't even looking for in the background. In other words, James Webb took us on a journey into the unknown, with a new set of eyes. And when Webb's razor-sharp eyes focused on distant and primordial parts of the cosmos, the telescope captured something perplexing near the beginning of time that made astronomers' jaws hit the floor. They shouldn't exist, but apparently do. Monsters lurking in Webb's images then prompt a rethink of our understanding of cosmic history. Join us as we dig deep into how James Webb reveals a universe that even scientists find overwhelming. To start, it's helpful to recall what the James Webb Space Telescope was built for. On Earth, astronomers often build telescopes on mountaintops and in remote deserts for an unobstructed view of the sky. But the Earth's atmosphere still mars the view. Space is the ultimate mountaintop, as NASA explains. James Webb launched in December 2021 as the successor to the Hubble Space Telescope, and it improves on its predecessor in several ways. For instance, because of its huge golden mirrors and infrared cameras, it can make better observations of planets orbiting stars other than our Sun. But for this discussion, what matters is how it can observe farther back in time than the Hubble telescope. In astronomy, the farther away an object is in a telescope's mirror, the older it is, because light needs time to traverse such large distances. Some of the light James Webb captures is almost as old as the universe itself, dating back to 100 million to 250 million years after the Big Bang. The relatively infant days of our universe, which is believed to be 1377 billion years old. That light is so far away, it has been traveling nearly the age of the universe to reach us. So, when the Webb focuses its mirrors on a particular patch of sky, it can see through time. The farthest objects in the image are the oldest. Those in the foreground are more current. The images that contain this rich history are called deep field observations. And while they appear in two dimensions to us, in them, scientists can see how the universe has evolved. Before James Webb, the Hubble Space Telescope gave humanity its deepest look into the evolution of space. And in the Hubble images, scientists saw a pattern. As they peered farther back in time, there were fewer and fewer galaxies, and they were smaller and smaller. This makes intuitive sense. Just like fossils in the oldest layers of the Earth's crust represent more primitive forms of life, the oldest galaxies in a deep field image ought to represent more primitive galaxies. And they differ from modern galaxies because they had the shortest amount of time to assemble. They were like teenagers compared to the large adult galaxies of today. When James Webb went online, astronomers were eager to peer a bit more deeply into the past. They thought the pattern from the Hubble images would just continue. We thought we would maybe see a couple of more distant galaxies, but they would be very, very rare. But things didn't go according to plan. Instead, when James Webb turned on, it was apparent that there was a lot more light back then, and a lot more galaxies. As Caitlin Casey, an astronomer at the University of Texas, Austin says, "We really didn't think there was much going on there." As a result, not long after James Webb came online in 2022, astronomers' jaws hit the floor. "I remember thinking, this just can't be right," says Mike Boylan Colchin, a University of Texas Austin astronomer. The observations he's referring to would, to you and me, seem like little smudgy red blobs among a field of other smudges and blobs. But in his eyes, they represented a potential challenge to the story scientists have painstakingly constructed about the formative years of our universe. That is, sometime after the Big Bang, around 12+ billion years ago, when the universe went from a dark, diffuse place full of gas to a light-filled universe populated by stars and galaxies. This is the era that laid the foundation for everything to come, including our solar system and you and me. Scientists had some theories about what happened during this crucial period, but the arrival of James Webb put them to the test by observing regions of space humans have never seen before. And even though the galaxies appear to our eyes as smudgy blobs, scientists can study the quality of light coming from them and make inferences about their size and age. Early analyses revealed many of these galaxies were apparently huge, full-fledged adults, not teens. We have found really mature, large, bright galaxies back even farther than we expected, Casey says. To further the fossil metaphor, it would be like finding evidence of advanced life forms in layers of the Earth when life ought to have been just starting out. In more fun terms, Casey explains it's like, at the earliest times, the universe was having a party, and we had no idea it was happening. Okay, you might be thinking, so what? We got big, bright, plentiful galaxies way back near the beginning of time. Unexpected, perhaps, but it's not like it's violating the laws of physics, right? Well, the problem is time. As Casey says, we're really starting to butt up against the age of the universe itself. They've had very, very little time to assemble. It's kind of like if you were flipping through a family photo album and came to the realization that your grandmother grew to be an adult from an infant in just a couple of months. Such a finding might make you wonder if we're missing a big piece of understanding human development, or somehow the pace of human development worked differently in the past. If these galaxies contain the number of stars implied by these early observations, it should be nearly impossible for them to exist. It would require all of the gas in the system being converted into stars, which is something you never see kind of anywhere in the universe at all. So even in the galaxies that are really intensely forming stars, we see more gas than stars. Gas is always left over in the process of forming stars out of it, which is to say, even more simply, these James Webb observations, on their face, make no sense. So, what explains these bright, large galaxies? The short answer is, they don't yet know. As Casey says, I cannot even get across how mind-boggling the past year has been of looking at James Webb Space Telescope data. We have been seeing all sorts of wild, wild things in the early universe. That's also why many scientists were agog, that if the observations were correct, everything we know about cosmology is wrong at some level. In other words, stunning discoveries made by Webb could lead to a wholesale rewriting of the history of time. Most scientists agree there's something big to be learned here, and it is these moments in science when observations don't match predictions that are the exciting ones. They often pave the way for fundamental new insights, and the more unexplainable, the more exciting they are. We've experienced these exciting chapters in science before. In the 1960s and 70s, when Vera Rubin observed galaxies rotating at unexpected rates, it opened the door for the discovery of dark matter, a hugely important, deeply mysterious substance that makes up 85% of all matter and acts as the scaffolding of the universe. And then, an unexpected observation in the orbit of Mercury in the 19th century could only be resolved when Albert Einstein reconceptualized our understanding of gravity in the 20th century. These moments of "this can't possibly be right" often lead scientists to uncover deeper truths or reveal new, uncharted depths of their collective ignorance. But while most astronomers believe there is indeed something odd about these galaxies, a note of caution: it is still early, and more observations need to be done to confirm their age and size. As Christina Williams, an astronomer at NOIR Lab, says, we don't have enough data yet. We have to keep in mind that the amount of data James Webb has produced is actually just probing the tiniest fraction of the universe right now. We have very small areas in the sky that we've looked at. Some of the excitement around these galaxies might dim with more time. But if they are verified, scientists need to figure out why they are there. The scientists outlined a few possibilities ranging from small tweaks to our understanding to, as Boylan-Kolchin calls them, the most disruptive options. What's so exciting is that each option is its own fork, leading to new questions, new possibilities, and new understandings of our science or the universe. Option 1. It's possible that stars and galaxies just formed differently, and perhaps more efficiently, earlier on in the universe. In the words of Casey, if you think about the early universe, it's a really dark place compared to where we live now. There were simply fewer stars and galaxies. And that light actually impacts how stars form out of new gas clouds. It makes it harder sometimes to form stars. In the early universe, those floodlights are not on, and so you could form stars really, really quickly, in a way that can't happen today, because right now the floodlights are on. The idea is that starlight itself impedes the development of other stars. As Boylan-Kolchin says, maybe that slowing down of star formation didn't happen in the early universe, which then led to these massive galaxies. But exactly how, the scientists aren't sure. Thus, this option would be unexpected, but wouldn't require a fundamental sort of revision to everything we know about galaxy formation and cosmology. Option 2. What if it's not stars that are making these galaxies appear so bright? According to Casey, the alternate explanation is also really confusing. Instead of a huge mass of stars, maybe we're looking at some of the most massive, supermassive black holes. It's confusing because James Webb is still observing galaxies. But there is a situation where the light might not be coming from stars, and the alternate option is that light is coming from a very, very hot disk of material that is being sucked into a giant black hole. And that disk of material is so hot that it shines really brightly. It can even, in some situations, outshine the galaxy in which it lives. This explanation solves some problems. As Aaron E. Lambrides, an astrophysicist working on a NASA fellowship, explains, if you assume all the mass in the galaxies is due to black holes, you get much more reasonable stellar masses that don't break the universe. You don't need to account for weirdly efficient star making, but this solution deviously opens the door to other vexing questions that could break our understanding of the universe in other ways. Their question: why the heck are there so many supermassive black holes in the early universe? Scientists know supermassive black holes play some role in galaxy development. But if these Webb observations represent black holes, it blows our estimates of how many powerful, massive, supermassive black holes at this time should exist out of the water. We do not know how the black holes got so massive so fast. Again, the essential problem here is the observations aren't matching expectations, which makes scientists think they are missing something in their understanding of the universe, something potentially very big. Option 3. The most extreme possibility is that scientists are missing a big piece in their understanding of cosmology. Cosmology is one part recipe, one part narrative for the creation of the universe as we see it today. Scientists can take the earliest possible observation of the afterglow of the Big Bang, which represents a universe before stars existed. They take that image and, using what they know about the properties of the universe, such as gravity, electromagnetism, tell the story of how the universe came to look like it does today. Scientists know the story is incomplete. Huge portions of it, like dark matter, a mysterious form of matter that seems to hold galaxies together, and dark energy, an even more mysterious force behind the acceleration of the expansion of the universe, are still not fully understood. But maybe this story is also incomplete in ways they had not previously considered. This is the most radical option. Boylan-Kolchin points out that It's very hard to see a wholesale revision to our picture of cosmology because it's so successful in so many different ways. Even their incomplete story can explain a lot of why the universe looks the way it does today. The new James Webb observations could be resolved by tweaking the cosmological model. Some of the tweaks could end up changing the estimate of how old the universe is. Or it could be that dark matter and dark energy are more complicated than scientists previously understood. In short, like Boylan, Colchin says, all of those options are disruptive in some way. Or, and this brings us to option 4, there is some other component of the universe that we haven't even accounted for that's out there. At that time, perhaps some people will wonder that why does it matter if scientists figure out which option it is? The universe, put simply, was not built for the human mind to understand, was it? Frankly, that statement is not wrong. But remember that finding our place means tracing the history of the cosmos. As Lambrides says, if the world around us depends on what it took to get to this world, we need to study that path. Why Earth? Why the Milky Way? Why the solar system? Much of that is rooted to the very first beginning of the universe. It's like humans have been put into a puzzle box of the universe. And the deeper we look into it, the more confounding it often becomes. It's going to take a lot more careful observations of these galaxies to narrow down the possibilities and figure out why they are so bonkers. And the good news is there will be time to do it. James Webb is expected to remain online for up to 20 years. Answers won't come quickly or easily, but to the scientists searching for them, they are simply tantalizing. It's the pure thrill of exploration. As Rohan Naidu, an MIT physicist, says, imagine, right, the wonder of the first person who set foot on Antarctica and saw penguins there. That's kind of like the vibe that is happening right now. We're just at the beginning of observing this era of time, which again was previously obscured to us. It took thousands of people to get that telescope launched, and it's going to take thousands of people to understand the data that came off of it. We've got a ways to go. In recent groundbreaking finding, astronomers have accidentally discovered a dark galaxy filled with primordial gas untouched that appears to have no visible stars. The researchers behind the discovery say this galaxy, designated J0613+52, could be the faintest galaxy found to date. Interestingly, scientists using the Green Bank Telescope, or GBT, discovered the dark galaxy through a complete error. According to Green Bank Observatory senior scientist Karen O'Neill, the GBT was accidentally pointed to the wrong coordinates and found this object. It's a galaxy made only out of gas. It has no visible stars. Stars could be there. We just can't see them. Remarkably, this galaxy full of primordial gas isn't billions of light years away, and thus seen as it was when the 13.8 billion-year-old universe was in its infancy. Instead, the dark galaxy designated J0613+52 is just around 270 million light-years away. This dark primordial galaxy was discovered by astronomers as they surveyed hydrogen gas in several so-called low-surface brightness, or LSB galaxies, using several major radio telescopes around the globe. LSBs tend to have a tiny population of stars spread across their volume, and as a result, they emit much less light per unit of area than standard galaxies like the Milky Way or Andromeda. LSBs are often barely brighter than the background luminosity of the night sky, making them incredibly tough to spot. LSBs also seem to be evolving much more slowly than other galaxies, with many still experiencing early stages of star formation. Astronomers believe this is because of their low gas density, meaning that overdense clumps of gas can't coalesce to that eventually birth stars. The aim of the survey that found J0613+52 was to determine the mass and gas content of these low-brightness or ultra-diffuse galaxies, the diluted nature of which causes issues for current theories of star formation and galactic evolution. astronomers noticed a disparity in data between the GBT and the Nancy radio telescope that would lead to the discovery of a galaxy that is an LSB, unlike any other in the LSB survey. According to O'Neill, what we do know is that it's an incredibly gas-rich galaxy. It's not demonstrating star formation like we'd expect, probably because its gas is too diffuse. At the same time, it's too far from other galaxies for them to help trigger star formation through any encounters. She added that this means that J0613+52 appears to be both undisturbed and underdeveloped, hinting that what O'Neill and the team may have discovered accidentally in the shape of this unique galaxy is the first nearby galaxy made up of primordial gas. This means gas made up of mostly hydrogen and helium created shortly after the Big Bang, which has not been enriched when stars exploded and seeded it with heavy elements, or metals. This is something astronomers would normally see further away and thus much further back in cosmic history. Also remarkable about this galaxy is the fact that it appears to be turning just like a normal spiral galaxy would. Ultimately, the discovery of J0613+52 has left its discoverers with more questions than answers. Primary among these, are there any more LSBs like this out there, or is this a unique galaxy? The short answer is yes. As O'Neill concluded, a full sky survey by an extremely sensitive instrument like the Green Bank telescope could uncover more of these objects. In addition, a new Hubble Space Telescope image shows the tiny galaxy UGC 5189A, located about 150 million light-years away in the constellation Leo in stunning detail. The Space Telescope, which has been observing the universe in infrared since 1990, has been studying this galaxy since 2010, with scientists using this investigation to learn more about a supernova that occurred in this galaxy over 150 million years ago. Over just 3 years, this supernova called SN2010JL emitted at least 2.5 billion times more visible energy than the Sun released over the same time frame across all wavelengths. Hubble officials wrote in an image description that SN2010JL is a Type II supernova, meaning that it marks the death of a massive star that, during its life, would have had a mass of at least 40 to 50 times that of the Sun. These explosions occur when these massive stars have run out of the fuel for nuclear fusion, and the energy that for millions or billions of years supports them against the inward push of gravity ceases. While studying supernovas themselves is of immense value to scientists, examining the wreckage that these cosmic explosions leave behind can be equally fruitful. For example, studying the environments around detonated stars can show the conditions needed to drive a supernova and how that supernova changes its surroundings. This interest means Hubble has found itself directed at UGC 5189A many times. This new picture is created from data collected during the long-serving Space Telescope's last 3 observation periods of the distant galaxy, which is just 36,000 light-years across, making it diminutive compared to our 100,000 light-year wide galaxy, the Milky Way. The image shows UGC 5189A as a flat, somewhat misshapen disk with a warped upward curve. The right-hand side of the galaxy is marked by blue fizz that represents plumes of bright gas and dust. The left side of UGC 5189A is less dramatic and striking, slightly dimmer with patchier coverings of gas and dust. Outside the main bright disk of the galaxy, a dark coffee-colored trail of gas underlines UGC 5189A and leads up away to the top left-hand corner of the image. While the background of the galaxy is mostly dark, a few small galaxies can be seen punctuating the inky blackness, and one star is clearly visible in the top right-hand corner of the Hubble image. Interestingly, Hubble hasn't just been studying UGC 5189A to zoom in on supernova wreckage. The Space Telescope has also examined several other supernova-hosting galaxies located around 1,000 million light-years away, that saw stellar explosions in their recent pasts, at least as we see them. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.